In this little video, I'm going to describe a property known as the inductance of a solenoid and a process called self-induction. I actually hinted at it in my earlier screencast on magnetic induction in a solenoid. So I'm going to refer back to that. If you haven't seen it yet, it's at the very, very end, and it might be worth a look. This is going to describe partly why you can't suddenly turn the current up or down or on or off in a solenoid. If you look very carefully at the current running through a solenoid, you will notice that it never spikes very quickly or turns off very quickly, and that's because of the self-induction process. So let's take a look. Well, here's a typical setup for a solenoid. We've got some power supply that it's plugged into, and we've got a little green region there that just describes maybe the plastic core that these wires are wrapped around. Kind of a crude drawing, but it works. I've shown 10 volts here on our power supply, and here's the plus terminal. So conventional current we have going this way, and if we look at the current in the solenoid and each of the wires, it's going kind of downward, and it's going to be important to know that. And so when it loops back up, then it's coming downward through this wire. So when current is just flowing through the solenoid at a steady rate, there's really not much very interesting about it. But what's really interesting is what happens when you first turn the power supply on and you go from no current in the solenoid to attempt to get a bunch of current through there. Let's think about why this happens. As soon as you start to flow current through the solenoid, then it is going to create its magnetic field inside there in that green region. But let's think about this little coil right here on the end. So suddenly that loop has no magnetic field, and then it has some magnetic field. Well, that of course is a changing magnetic field, and if we multiply that changing magnetic field by the area through which that field exists, then we will get the EMF generated in that loop that I pointed to. And in fact, I could point to any loop in there. So every loop feels that changing magnetic field created by all the other loops in the solenoid. So the difference here, and the reason we call it self-induction, is because the solenoid is both the producer of the field and the loop that feels that change. But the effect is the same nevertheless. We induce an EMF. That's kind of like a voltage just in the other direction. While we're trying to get current to flow downward through those wires, then we've got this little EMF that is opposing that. Now, I don't like in the textbook that he says that it induces a current in that direction. Well, that makes it sound like you have current going both ways through each of these wires, and that's just not right. It induces an EMF that just opposes the big EMF from the power supply, the 10 volts that we've shown here. So let me derive the expression for this, and then at another time we're going to show how to figure out exactly how much current would be flowing. So we throw a switch on the power supply. Well, if we're inducing this EMF that opposes it, how are we going to know how much current that is? That's kind of a separate issue. I'm going to take a slightly different approach than how Dr. Knight does in his book, but I think we're going to get to the same place. First, I want you to recall how big the magnetic field inside a solenoid will be and how it relates to the current going through there. So it's mu naught times the number of turns per length times the current. Small I or big I doesn't make a difference. I usually write this with a little n, but because I'm going to use big N in another way here, I want to show the total number of turns per length instead of little n, which is what it means. So that's the field, and so while that field is changing, while you're turning up or down the current in there, that's when you're going to induce this EMF. Now I'm going to leave the negative sign off of this here because remember that's kind of a separate thing. We're looking just at magnitude. And I pointed out that every turn of wire in that solenoid is going to feel the effect of this changing field. So that means we really don't have just one EMF. We have n times that many EMFs, each one produced by the changing magnetic flux due to the entire solenoid. And so if we write an expression for that changing magnetic flux, I'm only going to include the part that's changing inside my derivative. Everything else, the mu naught, the N over L, the area, remember area is part of flux as well, all those are just parameters that aren't changing, so di dt is really the only thing we need in our change factor. So if we simplify this, just combine some things together here, we get mu naught times n squared times the area. Now in this case, that's going to be the area of the circle formed by each of the windings. In the past we had to worry about, is this the area of the big wire loop around the solenoid or the area of the solenoid itself? But in this case, we only have the solenoid. We don't have a separate wire. And then we've got all this over L. And then here separately is the di dt. I'll show you why I'm keeping this separate. Get a little space here. What I want to point out is that all of this stuff here is just the physical parameters, the measurements that make one solenoid different from another. It's the number of turns, it's the cross-sectional area of the circle, it's how long it is. And so once we have a solenoid built, we pretty much have established what all of that stuff is. So we group this together and we name it the inductance of the solenoid. Inductance. And we use the symbol, my apologies here, the symbol is L. So if you don't like the symbol L, don't blame me, I didn't come up with it. So usually what we do is we write Faraday's law. In the case of self-induction, I'll include the negative this time, L di dt. It turns out that what we're going to do when we put these coils in circuits with other things, it's most convenient to have it in that form. So if you want to think of what L describes, it's a measure of how much a solenoid opposes very rapid changes in current. So when you try to flip the switch on and you've got it up full blast and you try to just blast a bunch of current through that solenoid, it is going to oppose it the most. And when you very gently try to bring up the current, then it will oppose it the least. And interestingly enough, then when you try to shut the power off to that solenoid, it does exactly the same thing but in reverse. It says, okay, so you're trying to stop the current flowing through me. I'm going to induce an EMF in the same direction that that current is to try to keep it going. So solenoids not only try to oppose starting current going through them, they oppose the stopping of current going through them. So I guess you could summarize it by saying it opposes any rapid change in the current moving through there. So we'll use this form when we incorporate these inductors, as we call them. We called them solenoids in the past, and usually when we put them in a circuit we call them inductors. And I'll show you how that equation or expression for the EMF is so helpful when we've got it in a circuit with other things as well.